Another technique to prevent overfitting is to regularize the weights of a neural network model. Now, it makes sense to bring in a very unrelated theory called Occam's razor. So, what Occam's razor says is given two explanations for something, let's say why something happens, the explanation most likely to be correct is the simplest one. So, simplicity rules. That is the explanation that makes fewer assumptions. So, it's a general theory. I mean, it's funny as well, but the razor simply says that simpler explanations are more likely to be correct. If we think from that perspective, then it makes sense to say that simpler models are less likely to overfit than complex ones. Now, a simple model in the context of machine learning is a model where the distribution of parameter values has less entropy. That is the model with, or a model with fewer parameters. But even if the number of parameters are same, we want the model with lesser entropy. So say we were looking at the distribution of the weights in a neural network, then if the weights are distributed all across, with a very large range of values, then this probably is a model with a very high entropy, and this is not probably a simpler model. Whereas if we came up with another model that had much simpler weight distributions, then this model probably is a better model than the first one. So then, how to reduce the complexity of a network to make it simple by trying to follow Occam's razor without actually changing the number of parameters? The idea is we can force the model to have its weights to take only small values. So maybe we can force that the weights must be always between, let's say, 0 and 1, or maybe 0 and 10, or something like this. We can force the weights to take only certain values. With this, what this is going to do is it will make the distribution of weight values more regular, more smoother, and in this way we will obtain simpler models. So what does weight regularization mean here? So when we say weight regularization, what we mean is we want to add to the loss function of the network a cost associated with having large weights. That is, don't let the weight values grow. So if you remember, basically loss is calculated by using prediction minus, let's say, true, and maybe we square it or difference it, whatever we do, absolute value. This is how loss is calculated, right? So the model updates its weights based on how bad or how good the prediction matrix P is, or the prediction values are. Now, the idea behind weight regularization is so this is our loss, right? We want to add a component that penalizes large values of weights. Now, of course, when the model is optimizing, it doesn't make sense to have all the weights to be very low. Then the model will think, okay, so if I have all the weights equal to maybe 0, then the loss will be very low. So we don't want this. We still want the model to focus on this. This is the main loss. So this is the main problem that we are solving, right? But we also want the model to focus on this. So this is secondary, but we also want the model to focus on this. So given at some point, if the model can obtain very low loss on the actual data set, it will then focus on obtaining a model with more simpler or weights that are within a certain range and less than a certain value, or following a smoother or a simpler distribution. So that's the intuition or the key idea behind weight regularization. Now let's look at two of the concrete ways to regularize weights. And those are known as L1 regularization and L2 regularization. What do they mean? So L1 regularization is simply adding a cost to your loss function, adding a cost such that the cost is proportional to the absolute value of the weight coefficients. So we simply add the weights. We simply add all the weights, W1 plus W2 plus W3, etc., to our loss function such that the loss now obviously will be higher, but it will also try to optimize these weight values such that these weight values start becoming smaller. L2 regularization is similar, but here we add a cost that is proportional to the square of the value of the weight coefficient. So we simply have W1 is squared, W2 is squared, W3 is squared, etc. And L2 regularization, because this is more popular, is also called weight decay in the context of neural networks. Now here's an example. Say, for example, we have a TensorFlow code and we have, let's say, conv2D layer. And what we want to do with the model is the kernel, the filter weights should be regularized. That is, the filter weights should not blow up or become too big from the whatever the distribution that they're having. So then we can simply add a parameter kernel regularizer equals regularizers.L1. So in this way, we are forcing the conv2D model to add this L1 regularization to the weights of the filters. Now, similarly, maybe in the next layer, we want another regularizer. I can do kernel regularizer equals regularizers.L2. In this case, I'm specifying L2. Now, when you're specifying regularizers, we can also optionally specify the weight of the multiplier for the weights. So what this means is every coefficient in the weight matrix of the layer will be multiplied by this value before being added to the loss function. So here, this 0.01 means that we multiply all the weight coefficient values with 0.01, and then we add it to the total loss of the network. Now, regularized models train way more smoothly than unregularized models. So here's a plot that shows the difference. So here, the cross points represent the validation loss of a model over epochs, and you can see that it's jumping back and forth or much more unstable compared to the L2 regularized model, which is much smoother. Now, one of the things that you may notice is that the regularized model actually has overall higher loss than the non-regularized model. So this model has higher loss and probably lower accuracy than the model without regularization. So usually regularization, of course, comes with a cost. Your loss may become higher than the lowest possible loss without original model. But what we want to do is continue to change the parameters of this regularizer, L2 regularized model, such that we still get lower loss, but then still the curve is smoother. So the goal is to get lower loss, get the same lower loss, but also have at the same time smooth curves.